This was surprisingly highly requested, so I'm gonna be doing it. This is going to be the science reviewer for term 2. I did one for term 1, so let's just get started. Thankfully, it's not too long, so hopefully it doesn't take us a while. First, we're gonna go to atomic structure and go to subatomic particles. So when you think about an atom, you should always remember these 3 subatomic particles. So let's list this down. So, in the modern atom, we know that there's a nucleus, and inside the nucleus, there's 2 types of type of subatomic atoms. So I'm gonna draw what I believe is to be an atom. Just a rough drawing. So we have this over here. So the red ones are called the protons. The protons have positive charge. Meanwhile, the gray ones are the neutrons, which have no charge. Just there. And the ones that orbit them are called the electrons. These have negative charge. So all of these play an important role to the atomic number and atomic mass, which we'll be discussing later. But let me show each contribution. Other terms as well. So first and foremost, the charge of an atom. Charge is defined by... not really charge of an atom. The charge of an atom is always 0, because otherwise that would be an ion. So charge of the atom is always neutral. Therefore, the amount of protons is equal to the amount of electrons. Meanwhile, the mass number of the atom is equal to the amount of, I'll just write P, protons plus neutrons. And yeah, that's all what you really need to know. Yep. And the atomic number is equal to the protons. So using this, we can use to solve the problems here. So these are the subatomic particles. Just remember their charges. Protons have positive, neutrons have nothing, and electrons have negative charges. The charge of an atom is the protons equals electrons, and this is the other formulas. Even with just as little as this information, we can already solve the problems here. So I'm just gonna pull out a periodic table. I'll attach it somewhere. I'll attach it somewhere here. So yeah, be right back. So I now have my periodic table here, so which means we can start already. So this table is what's probably gonna be in the exam, so make sure to listen up and check. So we know that these will not be given, by the way, so you have to know this. But if you know these, this is basically a given. So first and foremost, in number 1, we only have the atomic number and mass number. Let's start by naming the element based on its atomic number. The atomic number is going to be this number over here. As you could see, these are all abbreviated, but I'll tell you the names of them. We just need to take a look at the number. In this case, it's 35. So 35 is Br, and that stands for bromine. Now we have the atomic number. What we can also find from the atomic number is not just the name of the element, but also the protons, which is 35. So since we know it's 35 because the atomic number is equal to the protons, as you could see over here. Then, for the mass number, it's just protons plus neutrons. We know that the mass number is 80, and we already have the protons, so it's just 35 plus the amount of neutrons. By transposing 80 to the other side, it becomes 80 minus 35 equals neutrons. And by evaluating the other side, we get the amount of neutrons, which is just 45. So therefore, the amount of neutrons is 45. And since this assumes that all of these are neutral, that means that the charge of it's always protons equals electrons. Therefore, to solve this one, we just have the protons equals electrons and just 35. So the next one is we only have the atomic number and the amount of neutrons. So first we have the atomic number, which is 3. Once again, we can find what is number 3 over here. Number 3 would be Li, standing for lithium. Then, once again, just like what we did with the atomic number for bromine, you can also use the atomic number to find the amount of protons because they're just the same. So it's 3. Now, we also, since protons are 3, since this is neutral, it means the electrons are also 3. Then, when we find the mass number, we just add the protons and the neutrons. So 3 plus 4 is 7. Now, before we continue, I'd like you to review, use the methods we use, and pause for a little bit here. Give yourself about, I'd say, 5 minutes to solve. So hopefully you're pausing the video now, because in 5, 4, 3, 2, 1, I'll be showing you how to solve it. Okay, for the second one, we only have the mass number and electrons. Since protons is equal to electrons, therefore, electrons is also equal to the amount of protons. So we can also apply that logic here. And since protons is equal to the atomic number, we can also put 7 for the atomic number. Using the atomic number, we can also find the name of the element, which in this case is 7 for N. 7 is nitrogen. Then, once again, we have our mass number, we have our protons, but we don't know our neutrons. So we know the mass number, which is 14, so therefore 14, and we do know the protons, so 7 plus neutrons. Let's just transpose 14 to become minus 7 equals neutrons, and 7 is equal to the amount of neutrons. So therefore the answer is 7. Next, we have only the mass number and the protons. To solve this, we just need to find the atomic number first, which in this case, protons equals atomic number, so it's 10. Therefore, the atomic number is 10. We can use this periodic table to find it. The answer is going to be neon. Then, we have to find out how many neutrons and electrons. So, for electrons, we also know that's the same as protons, so we can just put 10 there. Protons equals electrons. Lastly, we're just going to substitute this once again. Since mass number is equal to the amount of protons plus neutrons, our equation could be something like this from the given already. Then we just transpose to find the rest. Therefore, the neutrons is equal to 9. So as you could see here, we kind of broke the pattern of, as you could see over here, we can't say protons is the same as neutrons, because as you could see, sometimes it's the same like in nitrogen, but sometimes it's different for the other elements. Lastly, we only have the mass number and the electrons. So we can always just do electrons equals protons because atoms are neutral. So therefore, this is 26. Protons is equal to the atomic number, which means we can also put this at 26. Now, we're going to do the same thing as we always do. We know that the mass number is 56, and then we already have 26 neutrons. So this has to, protons, so this has to be the neutrons. So 30 is equal to the amount of neutrons. And atom number 26 is Fe, which is iron. So that's really all for an entire cycle's worth of lessons. It's it's relatively simple actually. The more challenging part gets to when the last two topics for me, in my opinion, is the hardest. No, just the fourth topic. So all you need to know in total for subatomic particles, atomic number, and atomic mass, we just need to, yeah, we just need to remember that these formulas and the charge of each atom. So yeah, very good. We just managed to finish an entire unit. Okay, I'll need to bring out a different periodic table, one with more detail. Okay, so it's time to talk about. I'm going to now talk about the periodic table, and I'll highlight each one for you. I'm gonna have a red circle encircle what are we focusing on right now. So let's start with the alkali metals. These alkali metals are, well, they actually exist as compounds. So you will not really find just a lone of these. They really will be in a compound. When I mean compound, it's like part of another compounds. They're part of another atom, like another set of atoms. And these actually are very reactive. Most especially to the halogens at groups 17. Then its density is low, as well as the melting point. So what we can learn from these alkali earth metals is just they're very reactive and they have low density and melting points. Okay, I think we got that. Next is the alkali earth metals. Once again, not to be confused with the alkali metals, but they do share a few commons. Like once again, they are highly reactive. But they're also solids. They exist as solids. They're harder than the alkali metals, so more dense, higher density than group 1. And despite not being like, despite not having this, they're still part of the metals. So they have the metals properties. They have the metals properties, which means shiny, they're lustrous, they are heat and electricity conductors. So that's what we can learn from group 2. Once again, they're going to be highly reactive, solid, higher density than group 1, and they are shiny, lustrous, heat and electricity conductors. Okay, I forgot to erase the red line, so we just have to deal with that now. But the next one is gonna be the biggest group, called the transition metals. And these are the ones that get really confusing later on, so take note of these. These for now are just hard, shiny, and lustrous. And they are high melting point, as well as being able to conduct electricity. So that's what you really need to know. It's very general. It's very much what you expect from a metal. Once again, it's going to be shiny. Sorry about that. It's going to be a shiny. That's just a little map I made, but it's going to be shiny, lustrous, high melting point, and conducts electricity. So what's next? I've covered most of these now. We're actually going to skip the lanthanides and actinides, unfortunately. So the next 4 groups, they don't really have a name, as you've seen. We just call these boron, carbon, nitrogen, and oxygen family, respectively. These are the earth metals, tetrals, pentogens, and chalcogens, respectively. They don't really have any specific properties through their groups because they're all part of different classifications, as you could see here. But yeah, just make sure you know how to name them. Next is group 17, which is the halogens. So halogens, if you heard from the periodic table song, it's they react aggressively with metals, especially G1 and G2. They have poor conductivity in general, and yeah, low boiling points. Sorry, low boiling points. I just have to do cursive now. There, low boiling points. So that's what we can just learn from these halogens. They react very aggressively, especially with the alkali metals. They have poor conductivity and they do have low boiling points. And for the last one that we're gonna be discussing today is the what's this one? This is going to be the noble gases. The noble gases are the ones in white, and very much they're actually super stable, and we can't really say them. They're like colorless, odorless, and they're not flammable. And they were so stable and so like unreactive that these were initially called inert gases. So they were so stable. Just remember that the noble gases are the pinnacle of stability in the periodic table. And really, as long as you memorize the four groups at the start at the beginning, like group 1, 2, 17, and 18 is really all you need to know here, you should be fine on the test. And we could very much tick this arrangement off. Now, this may vary from periodic table to periodic table. So we do have, once again, just gonna reiterate, this is the group and this is the period. So these are the periods and these are the groups. So once again, you might see an element like this. So I'm gonna show you the structure. So H would be your atomic symbol. Then 1 would be your atomic number. This would be like the atomic name. And the number below here shows its atomic mass, which is rounded off. So this is just an example of hydrogen. So we have the symbol, the name, the atomic mass, and the atomic number. So that's all the features of the periodic table, if I'm not mistaken. There will be more when we go through later, but it's time to talk about a fairly tricky one, periodic trends. So I need to write quite a lot of stuff here. So let's see. I'll see you in a bit. So the next two trends here are atomic and ionic radius. They both follow the same trend of increasing from top to bottom. So as you can see, I've made a visual representation of the atomics, the atomic radius, So atomic radius, as you could see, it gets larger from these top to bottom. The reason why is that as you move along these periods, right, you'll have the nucleus here and another orbital, which we'll discuss later, then another, so it gets further and further away, as you could see. So that's why the radius gets bigger. However, from left to right, it decreases until here. Why, you may ask? Because you got the electrons here, and the bigger the nucleus, it's like pulling them towards here, so it's closer. Like once you have a big enough nucleus in the almost rightmost, you'll have like this atomic radius, like this. So that's why it decreases from left to right. So I'll give you an example here. So let's say out of oxygen, nitrogen, carbon, and boron, you're asked to find who has the most or the biggest atomic radius. So since it decreases from left to right, you want to find the furthest away from the right. So which is the furthest away from this line, let's say? Let's say which element is the furthest away from that red line there? It's definitely going to be boron. Similarly, you can still also apply even if they're not on the same row or column. So even if we do, let's say, oxygen, phosphorus, germanium, and let's say silver. As you can see, once again, they're not really in the same what they call this period, but we can apply the left to right and top to bottom. So remember that it increases going this way in general. In general, atomic and ionic mass starts small at first from this corner right here in fluorine, all the way until you get the biggest one at cesium over here. So by going from this logic, you know that oxygen is the smallest and silver is the biggest because it's the furthest away from fluorine. Fluorine is a pretty handy element for locating stuff, to say the least. I'll explain why later. For now, all you need to know about atomic radius is that it's the distance from the nucleus to the outermost electron. Now, it gets a little bit complicated for ionic radius, but it's more or less the same thing. So, a cation is for these following elements here. Oh. Hold on. Wait. The image got deleted. So, I'll just restore this real quick. So, it's over this one. Can be this one over here. So, if I erase something, I'm so sorry. Yeah. Anions. So we have cations and anions. So, what are cations? These are for when an atom becomes an ion. This happens when it loses electrons. When you lose an electron, it messes up the charge. It's no longer a neutral atom. It's not even an atom at all. It's now going to be called an ion. This is what you call a positive ion or a cation. And it only happens for metals and metalloids. So once again, here it is. So these are the ones that are going to be affected by the considered cations. However, anions are for nonmetals. And this is when they gain electrons and end up getting bigger. So, once again, it messes up the charge because since you gain an electron, now there's an imbalance of electrons and protons. Hence, we put the negative symbol here. So, as you can see over here, we have all the different ionic sizes. Now, the same thing, it's kind of more complex than this one, isn't it? You're focusing on the gray dots, but once again, all you need to do is just treat the non-metals just separate them from metals and semi-metals and the non-metals. So, if we just have here, separate these elements over here and just apply the same logic. So if you're asked just here, focus on the same trend. So as you can see, increases from top to bottom and decreases from left to right. So as you can see there, it does increase from top to bottom, yep. And it just does decrease a little bit from left to right. So let's say you're asked to find phosphorus, silicon, fluorine. Which of these have the biggest ionic size? It's fluorine. Oh, sorry, it's phosphorus. Smallest is fluorine, biggest is phosphorus. Now you may start to notice a little bit of a trend here. It looks like the noble gases are kind of a rule breaker here. Same thing here. There's no ions here. We can apply those knowledge later in our chemical bonding. It comes in handy there. But for now, that's all for the first two periodic trends. Once again, the atomic and ionic radius both increases from top to bottom and decrease from left to right. So the next two trends we're going to be focusing are, and the last two, the final two, they're kind of like the opposite in terms on the table, but I'll explain them first. The first is the ionization energy. It's the amount of energy required to pull the outermost electron. If you paid attention from the table a while ago, I indicated that fluorine would be the lowest value for the ionic and atomic mass. But for these two trends, fluorine now seems to be the highest. Why is this the case? Because it's literally the exact opposite of the trend. The going up or going down trend is the exact opposite. This time it decreases from top to bottom and increases from left to right, the exact opposite. So now, once again, if we use our good old oxygen, nitrogen, carbon, and boron, we want to know which one has the most electron ionization energy or electronegativity. It's now going to be the one that's closest to this wall instead of the furthest. So in this case, it's oxygen. Once again, the same thing applies once again here, even if they're not on the same period. Oxygen, phosphorus, silicon, aluminum. Which one has the least electronegativity? Aluminum. Which one has the most electronegativity? Oxygen. Remember that fluorine is always a good indicator. So you want this time to be as close to fluorine to have as much electronegativity or ionization energy. But why is this the case then? Why does it take less energy to pull out, let's say, something from cesium? Well, cesium is so far that it actually has like 6 energy levels. So we have the nucleus and like 6 energy levels. Once you have so many electrons, you can't really hold on to them. You can't really hold on to those electrons, and therefore, sorry about that. We need to, well, it requires less energy to pull this one out because there's so many electrons and so many energy levels that nucleus is trying to attract, but it just can't hold on to it effectively. Compare this to the fluorine or the oxygen, where I stated that the atomic radius is so small that it looks something like this. So it looks like something like, wait. So we got the nucleus over here. Let's pretend this is an oxygen atom. The thing is, the big nucleus and the small amount of electrons causes them to be very close to one another. And because this distance is so small, it takes a lot more energy to pull them out. So as you could see, there's barely any electrons on this oxygen atom for I can tell. As you could see, you can't really pull that out. You can't really pull that. It's going to take a lot of effort and energy to pull that out. So that's why the trend happens. Now for electronegativity, it's just the tendency of an atom to attract electrons to itself. And once again, as you can see over here, it decreases from top to bottom and increases from left to right. Once again, fluorine being the most electronegative out of all of this. This property will come in handy later when we're doing chemical bonding. Both of these come important for chemical bonding. Now, one thing you might notice is why are the noble gases, they're not applicable to electronegativity. Well, it's because we attract electrons to create bonds, which we will explain later. But the thing is, the valence electrons of these are sufficient for them to be stable on their own. They have 8 valence electrons. The others have 1 through 7 valence electrons. So they need to bond somehow to make 8. And we'll talk about that later. For now, that's all for periodic trends. I'll return to you when we are ready with the electronic structure of matter. Okay, so this is going to be the next topic, and it's the quantum mechanical model of an atom. But first, how did we get to the atom we know today? Actually, these people are the reason why we know the atom, how we know it today. So the first one is the Greek philosopher Democritus. He didn't came with any atomic theory, but he did came up with the atomic theory, but we didn't really discuss it. He just stated that all type of matter is made from atomos. These are indivisible particles. So all matter around us is made of indivisible tiny particles called atomos. So he just came up with the word atomos. But this is the first concept of atomic theory. Then, quite a while later, John Dalton, an English school teacher, came up with Dalton's atomic theory, stating that all elements are made out of atoms and same element atoms are identical. Furthermore, atoms can't be combined to form compounds, and these cannot be divided further as stating from Democritus. So it supports Democritus' claim that it cannot be divided any further. So, this is where the first atomic model came from, but it isn't really a model. If you just look it up, it's actually just a bowling ball model, something just like a circle. It wasn't until English physicist J.J. Thomson developed the first type of atomic model. It's called the plum pudding model, and if you Google it up, it has two circles, and then it has plus, 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 and then it has this one, the negative, negative, negative. So we're gonna do here as well. We're gonna copy the same thing here as well. So this is the plum pudding model over here, and there's actually a bit of arrows here as well. So it looks something like this. This is called the plum pudding model. He stated that there is actually negative charges in the atom, which he was correct about. He discovered electrons. So just like how a pudding is just a mix of something, it's mixed. According to J.J. Thomson, the electrons that as we know today and the protons were mixed together, somewhat like a pudding. However, Ernest Rutherford would prove this wrong, as he discovered that they are not mixed like pudding. Instead, there's a dense sphere. This dense sphere, the one in the middle, is what we know today as the nucleus. So we're going to draw the nucleus over here. And around this empty space, he has like this orbit. He drew these orbits like this ellipse. I will draw a proper ellipse, okay? Hold on. So he drew these like ellipse. Don't fill them. So he drew it something like this. So there's like this and like this. It looks like something like this. So multiple circles, it's kind of what you know. If you think of atom, probably when you were a kid, it's probably something like this. You've probably seen this in Canva if you design quite a lot. And this is actually kind of close to what we know as an atom. So, there's just the electrons over there, here, 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 there. You know that. You all know that by now. So this is kind of correct, but no. Danish physicist Niels Bohr said, no, there actually is different like orbitals, different like how the planets revolve the sun. The electrons have different orbitals, and to a certain extent, he was definitely right about this one. So as you can see, he still has the orbit. So Niels Bohr model also still has the good old like orbits, right? But instead of this being like interlocked, it's now the atoms are like more in a fixed orbit. So we got this one here. There's like some over here, like maybe 8 over here. Yeah, like this, and there's more over here. So this is the Niels Bohr model. And once again, he stated that there's different orbital levels, as well as that atoms can have ground states, that's the lowest allowable energy, and atoms get to an excited phase when they gain energy. He also stated, I didn't write it here, but he also did stated that the smaller the electron orbit, the smaller the lower energy level. So yeah, he stated that these are stable orbitals as well. But we always know that there's something else, This can't be it. It can't be fixed. It can't be. And that's what German physicist Werner Heisenberg, said. So they basically said that there's no such thing as a fixed orbital. There isn't. That's called Heisenberg's uncertainty principle. You can't measure something. You can't measure something without disturbing it. So hence, instead of just fixed orbitals, there's no fixed something to begin with. It's just you got the nucleus over there, and it's just surrounded by this electron cloud where the electrons could possibly be there in these yellow dots that I'm drawing here, but we don't know for certain. And here comes the quantity mechanical model of an atom. It's the likely locations of atoms, but we do need to use the energy level, sublevel or subshell, and the orbitals to figure this out. Now that we know the quantum mechanical model of an atom, let's try to now know what is the electron configuration, which is a lot of calculations, and we do need different charges. Okay, so this is going to be now electron configuration. This is where it starts to get tricky, so I'm gonna slow it down a bit. Usually I'd go pretty fast, but yeah, I have to slow this down. So the first one we discussed is going to be the energy level, where it's a fixed amount of energy that an electron can absorb, and it's determined by EL is equal to the period number of an element. So once again, here's your period number, and remember, once you occupy elements in the, let's say, period 4, occupy the 4th energy level and everything below it. So like 5 occupies levels 1 through 5, 6 occupies levels 1 through 6, and so on and so forth. So you don't just say, when you're answering the question, you don't just say energy level equals just 4. You have to say 1, 2, 3, and 4. I'll show you that later when we actually solve. So and then finally we have the off-bow principle, which I'll illustrate right now. So we have these energy levels and the max electrons. It states that electrons must occupy lower energy level first before moving on to the higher levels. So this is the first energy level, the smallest circle. It can only occupy 2 electrons, so like that. Only once there's 2 electrons there, you can only put a 3rd electron here. So you can't do like this. So you have your first electron here. You cannot do this. You cannot put the 2nd electron there. That is wrong because you have not reached the max electrons for energy level 1. So now that we have the max electrons for energy level 1, now we can move on to energy level 2. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then only once we have 8 maximum, that's the maximum amount of electrons for the 2nd energy level, you can start to put your electrons down the 3rd energy level. So that's 18. So 1, and so on and so forth until you reach the 4th. We'll only discuss until the 4th because really we cut off the periodic table at around element number 54. So we don't really need any more energy levels higher than that. Now the sublevels are the shapes of the atom. It's kind of complex, but all you need to know is the amount of orientations and the maximum amount of electrons for each one. Sorry, I don't know if it's electrons, but yeah, electrons. So how do we solve for the electronic configuration? Well, there are 2 more rules we have to follow. First is the Hund's rule. Let me just write that down. Hund's rule states that we have to have one orbital filled first. So let's say we have 1s that only has one orientation, right? So 1s, no, let's do something different. Let's do 2p instead, 2p. So 2p has 3 orientations. Now, Hund's rule. So basically, we can't just do this. So the correct way to do this is that, okay, electron 1 goes here, electron 2 goes here, electron 3 goes here, then only once all these boxes have been filled, you can put a 2nd electron there, a 2nd electron there. So you can't do something like this. So you have first electron there, then second electron there. No, that's wrong. You have to put one more here and another one here to satisfy Hund's rule. So what is Hund's rule in general? Well, Hund's rule is just each orbital must have one electron before second filling. So I'll put a correct example and a wrong example. This is a correct example. Yeah, I'll just not put the wrong example. I think you guys get it. But yeah, you know, hope you get it. That's the Hund's rule. Then, similarly, well, not really similarly, but Pauli's exclusion rule, I'll just shorten it. It just means that two electrons, same orbital, with the same orbital, must have opposite spins. So let's take our, once again, 1s. And I'll take another, let's do a right and wrong. So this would be a correct example, and this would be a wrong example. So right there. So this is the correct example, and this is the incorrect example. So as you can see, I drew here the electron, and they have to make sure to have opposite spins, and not like this where they have the same spin. So finally, now we can start solving, and I'm going to be using just this space, okay? I'm going to be using this space to highlight it. First, let's start off easy. Let's start off very easy, okay? We're going to start off with the simplest element that we can do. Hopefully, it doesn't get too hard. So the first one is going to be, we need to write the element first. So we got the element name, we got the atomic number, and then we got this energy levels, the sublevels, the number of orbitals, and the electron configuration, of course. Okay. So let's start with helium. So helium is over here, and its atomic number is 2, and the energy level is N is equal to just 1, because it's only in the first period. Now here comes the tricky part. Let me just make this in another layer. Hold on. Whoops. Okay. So I've made another layer. So once again, helium is atomic number 2, as we see over here. Now, what you want to do to check, once again, the energy level is going to be just N equals 1, because it's in the first period. Now, sublevels. So you want to start from hydrogen, reading left to right, just how you do it. So hydrogen, and stop once you reach your target, helium. You see the different colors? I want you to count how many colors we passed by through. So from hydrogen to just helium, it seems like there's only one. And as you can see, there's letters there. Those are the sublevels. We don't mind the numerical coefficients for now, so just the S sublevel. For the number of orbitals, once again, so we have to count again. So hydrogen to helium. So we have a 1s here and a 1s over there. So it looks like we only passed by one orbital, 1s, which means it's just 1. How do we now find the electronic configuration? Let me just electron config. Okay, yeah. So how do we find the electron configuration? Now, one at a time, we're gonna count. So from So we only have, let's start from 1s and count how many 1s elements we took to get until we got to helium. So just 1 starting from hydrogen and 2. We're now already at helium. So it's going to be only 2. And that number you counted will apply to each orbital. But remember that this is the restriction of the electrons. S can only have a maximum exponent of 2 in this case. P is 6, D is 10, and F is 14. So as simple as that, the electronic configuration for helium is just this. 1s raised to 2, or 1s2. Let's try a more challenging one. This time, let's try for fluorine. Fluorine is over here, and it's F. Symbol is F, and the atomic number is 9. The energy level is once again determined by the, what do you call this? The period. So it's now in the second period, so it occupies both the first and second energy level. So therefore we put n equals 1 and 2. Now the sublevels, let's see how many colors, just colors for now, not orbitals, just colors. So we have blue over here for S, blue once again for S, and we finally arrive here at fluorine, and we discovered a new color, yellow. So S for the blue and the P sublevel for the yellow. So we now have 2 sublevels. Now let's count the orbitals. We have to pay attention now to the letters. So we got 1s. Zooming in, this is a different 2s. And zooming in until we get here, 2p. So we got 1s, 2s, and 2p for a total of 3 orbitals. Now, the electronic configuration. A tip to expedite the electronic configuration is that you just have to focus on the last one, the last term. So this is 2p. And then for these terms, the 1s and 2s, you can just put the maximum amount of electrons immediately. So 1s2 and 2s2. Then you locate your 2p over here on the periodic table and start from the first element in 2p. So boron is 1, carbon is 2, nitrogen is 1, nitrogen is 3, oxygen is 4, and fluorine is 5. So therefore, 2p5. When you're asked how many electrons are in an electronic configuration, you just have to add this number over here. So 2 plus 2 plus 5 is equal to 9. And if you did your electronic configuration correctly, it should be the same number as the atomic number. I hope you're getting the gist so far. So let's try to practice a little bit. Now that you have learned how the first, 10 elements work, I want you to pause and maybe use the comment section, or you can DM me if you know. Anyway, my task for you is to find the electronic configuration for nitrogen. So nitrogen has an atomic number of 7. From that, I want you to pause for, set a timer for 3 minutes, maybe 5 minutes if you're a little slower, and be back to the video and check if your answer is correct. So, I hope you're pausing the video right now, because in 5, 4, 3, 2, 1, I'll explain how to get the electronic configuration for nitrogen. So as I've stated, it's now number 7, element number 7 over there. And just like fluorine, just like how we did with fluorine, it's in the second period and does occupy as well energy level 1 and 2. So energy level is N equals 1 and 2. For the sublevels, once again, you just have to count how many colors you passed by until you get to nitrogen. So that's blue, blue again, and once again, we only have blue and yellow, which represents the S block and the P block. So S and P. Oh, sorry, I put it in the wrong spot. SP. Now the number of orbitals, once again, we're going to have to now pay attention to the numbers here. So this stroke for 1s, 2s, and 2p. So we have 1s, 2s, and 2p for a total of 3 orbitals. The electronic configuration, once again, let's apply the same tactic we use. So 1s2, 2s2, we apply the maximum amount of electrons for all the terms except the last term. Then we locate your last orbital, 2p. Then starting from the first element of 2p, count. 1, 2, 3. So it took us 3 elements of 2p to get to the nitrogen. Therefore, it's 2p3 for nitrogen. The complete configuration is 1s, 2s2, 1s2, 2s2, 2p3. I hope you're getting the gist by now. Now let's move on to where it starts to get a little bit trickier. Let's challenge ourselves and try to find let's try to find the electronic configuration for phosphorus together. First and foremost, phosphorus is most obviously 15 in atomic number. How about the energy level? So the energy level of phosphorus is in the third period, therefore it occupies all 3 of these energy levels, which means N equals 1, 2, and 3. How about the sublevels? How many colors did we get through before? How many colors did we pass along before we got to phosphorus? So we got blue once again, yellow, blue once again, and still yellow. So it's just the S and the P. So sublevels are S, P. Now for the number of orbitals. So this one gets a little tricky, but let's count together, guys. So 1s makes 1, 2s makes 2, 2p makes 3, 3s makes 4, and finally we arrive at phosphorus and pass by 3p for a total of 5. 1s, 2s, 2p, 3s, 3p for a total of 5. For the electronic configuration, we're once again going to do the same tactic. We're just going to we're just going to take note of all of this and immediately put their maximum electron count. So 1s2, 2s2, 2p is 6 because, as you can see here, max electrons for p is 6. So 2p 6, 3s2, and finally 3p something. Then let's locate our 3p and count how many tiles or elements we had to go through before we hit phosphorus. So aluminium is 1, silicon is 2, and phosphorus makes 3. Therefore 3p3. And that is the electronic configuration for phosphorus. Good job. If you're still getting it, you're doing great so far. This is the third out of the, I think, 4th level. Yeah, 4th level. I think we only go until the 4th level here. Alright. 4th level. It's just the same thing all over again, but once again, I'm going to explain it because it can get real confusing. Let's now find the electronic configuration once and for all. Let's try to find zinc. And we'll actually deploy a new tactic here because the configurations are getting really, really long. So, We know that the zinc's atomic number is 30. How about the energy level? The energy level is once again determined by the period. The period here is 4. So zinc occupies the first through fourth energy levels. N equals 1, 2, 3, and 4. Now we're gonna count how many colors we passed by before we got through zinc. So we got blue for 1, yellow for 2, blue again, yellow again, blue again, and finally a new color, red, for 3. So the red represents the D block, and it's dog, D as in dog. So we have the sublevels as S, P, and D. Number of orbitals. Okay, I need to shrink my brush here because that's a lot of orbitals. Let's count together. So we have 1s, that's 1, 2s. I'll make my brush bigger for this one at least, and red. Actually, no, purple. So 1s, so that's 1s for 1, 2s for 2, 2p for 3. Remember, we're at zinc, we're looking for zinc. So we're still at 3, 3s makes 4, 3p makes 5, 4s makes 6, and we arrive at zinc after a grand total of 7 orbitals, with the last being 3d. So let's list that down. 1s, I have to go small here, 1s, 2s, 2p, 3s, 3p, 4s, and 3d. That's a total of, yes, 7 orbitals. Once again, we're going to copy the same technique that I already taught you. This is the third time we're going to use it. Copy all the orbitals first. So except the last one. Copy all the orbitals first, except the last one. 1s, 2s, 2p, 3s, 3p, and then 4s. We're going to leave 3d first because it's the last one. Then immediately put the maximum amount of orbitals not orbitals, electrons for each one of these. So we got S is 2 and P is equal to 6. So we put 6 here. Then we locate 3D on our periodic table, and as you can see over here, let's just clear it a little bit here. So as you could see, we're gonna locate our 3D, and we start from scandium for 1, titanium for 2, vanadium for 3, chromium for 4, manganese for 5, iron for 6, copper for 7, nickel for 8, sorry, this is cobalt. Cobalt for 7, nickel for 8, copper for 9, and zinc. We finally arrive at zinc after passing by 3D, and that's 10 elements in total. Now you notice, these electron configurations are getting really long. How do we abbreviate them, you may ask? Now for the K, I'd say you just abbreviate if it's levels 4 and above. Otherwise, I don't think it's necessary. So we see zinc over here, right? So I want you to backtrack from this time, going behind, like going like this, follow the red line like this, until you stumble upon one of the noble gases. So the noble gases, for a reviewer, are this. So we're going to go trace back all the way back to potassium, and we hit argon. Now, argon has a number 18. Remember what I told you, that these exponents are actually the amount of electrons? Now, we can just erase a chunk of this until we have exactly 18 electrons. So 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. And 12 plus 6 is 18. So what did I just do here? Why did I cross out this? Well, we can just use the noble gases as a bookmark to store these long configurations. You can just use square brackets and just make sure to put the correct element. In this case, we used argon. Then copy the rest. So either of these configurations, I didn't add another layer, I'm so sorry, but either of these will be accepted. But if the test says to simplify using noble gases, this is the correct answer. Now, this is one of the topics where a lot of people really struggled in, and I understand why. So, for your assignment, I want you to find the electronic configuration, simplify using the noble gases. I want you to find the electronic configuration for selenium. I'll give you 10 minutes for this one, and set a timer for yourself, and I'll be right. I'll actually answer this in the comment section, or reply if you comment there. If you DM me, I'll also reply, or at least try to. So once again, write selenium down as your to-do list and accomplish it yourself. I'll explain to you how to get it once I try to see your solution and point out possible errors if you made any. And with that was a long one for electron configuration, but it only gets harder from here, I'll be honest with you. So we're going to switch layers here and mark, wrong. We're going to mark this green because we have already completed it. Okay, we're down to the last two topics, and these are the most difficult ones by far. Hope you're doing good so far. If you made it this far, thank you very much. Well, nearly forgot, but before we get into the actual hard part, we're going to learn some basics first about chemical bonding. So chemical bonding starts with the Lewis dot structure. It's basically a way of notating the valence electrons using up to 8 dots, following the 2 dots per side and 1 dot on each side first. Valence electrons are the outermost electrons. Any element can have 1 through 8, and what do you call this? A molecule needs to have, or an atom needs to have 8 valence electrons to achieve stability, just like how I said in the noble gases. The noble gases are stable because they have 8 valence electrons. However, bonding is needed to other elements that aren't noble gases. So therefore, we have ionic and covalent bonding. So, okay. So first, we're gonna show you in this later. But as you can see, that's the octet rule. 8 valence electrons to achieve stability. So I'm going to use the Lewis dot structure to see what's going on here. But first, remember that ionic bonding is a non-metal plus metal. Therefore, you're going to create ions. It's called the transfer of electrons, and this is a visual representation. It's kind of inaccurate. So here, the sodium and chlorine have equal electrons, but due to a chemical reaction, the chlorine received another electron, and this is now stable, and the sodium lost 1 electron. And because of this shift in electrons, one of them is now positive, the one that lost electron, and the one is now negative, the one that gained electron. The one that gains an electron is often the gas or the non-metal, and the one that loses the electron is often the metal. So let's use the Lewis dot structure. So from here, it's not really stated, but is it stated? Okay, yes, it is. So it is stated that, oh no, it's not stated, but the valence electrons are 1, 2, sorry, wait. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Correct. So we find sodium, that's going to be here. So it has 1 valence electron. So using Lewis dot structure, we just put Na, then 1 dot in any side you want. Then we find chlorine. Chlorine. In this case, it's chloride, but it's still chlorine. Chlorine has 7 valence electrons. So we do Cl. Then we first draw 1 dot on each side to follow the rule. Then we do 5, 6, 7. There. Now we have a Lewis dot structure for sodium and chlorine. And due to the chemical reaction, sodium or natrium lost an electron, so it's now Na plus, because in this sodium atom there's one less electron than protons. Meanwhile, in this chlorine atom, it's now a minus, and it takes the other electron of the sodium. And due to that extra electron, it's now a negative ion, but is now also stable because it has 8 valence electrons. Almost the same. So this is for ionic bonding. Remember, it's a non-metal and metal, and I will have to flash that. I'll have to flash this non-metal and metal. Oh, sorry, non-metal and non-metal. There. So I just realized my error, but yeah. So this is ionic bonding. It's the transfer of electrons. I'll tell you there's also another part we have to compute for. Next is a covalent bonding. The covalent bonding is the sharing of electrons. This happens when the electronegativity gap between these two elements is not higher than 1.7. I'll show you the table later. So, basically, it's made of nonmetals and nonmetals. So let's draw the Lewis dot structure again. Hold on. So the Lewis dot structure for this one would be, we have one H, and H has 1 valence. Then we got O, which has 6 valence. And we got another H, which has 1 valence. Then because of covalent bonds, it now looks like this. So we got H over here, and then we got the 2 dots over here, and then another H. It looks a bit weird, but I'll separate it. So you got the H over here and the O over there. Now what happened here? As you could see, the O has 6 valence electrons, but now here has 8. Where did the other 2 come from? It's from the assistance of these 2 hydrogens, and as you could see now, they're all connected into one clump to form a compound. This compound or molecule is called H2O, and it's more commonly known as water. Meanwhile here, as you can see, they're not connected, but they just have this positive-negative charge. So visually, that's the difference between ionic and covalent bonding. Remember that ionic is a non-metal plus metal, and covalent is non-metal plus non-metal. Here are the properties. So just remember that crystalline solids, once you have crystalline solids and high melting points, that's ionic. The reason why it has high melting points, it's because it has a metal in it. Furthermore, it can conduct electricity because of the metal as well. And since these are polar substances mostly, it's soluble in water but not in non-polar liquid. Meanwhile, in covalent compounds, these are just gases, liquids, or solids made out of molecules. Like I said, this is a molecule. This generally means that it's a lower melting and boiling points because gases or nonmetals don't really have the highest melting points. And because there's no metal present, it usually indicates poor electrical conduction in all phases. And this is the opposite of ionic because it's not soluble in water, but it is in nonpolar liquids. So there it is. That's the properties of ionic and covalent, the bonding, and the Lewis dot structure, and the octet rule. Okay, so that is ionic and covalent bonding right there, and and that's the properties of compounds based on chemical bonding. Oh no. This topic. I need to flash something. I'll flash a warning right now, probably right now in a few seconds, and I'll tell you why once we get there. Okay, here we go. So I'm going to teach you how do we name ionic and covalent compounds from word form to chemical formula and vice versa. Yeah, if you've taken the test before, you've probably seen these items, and I'm going to be explaining every single one of them, so this will take a while. Alright, so I'll flash it right now. Remember that ionic is a metal plus non-metal, and covalent is a non-metal plus non-metal. This will be up for the screen for the entirety of this section to make sure we don't forget it. Because of the confusion, this led to a drastic drop in scores. So we don't want that to happen during the ETA. So I'm gonna flash it right now permanently. So let's do this. So for ionic, we just do drop, swap, and reduce. But for covalent, we do the prefix system. However, we do add IDE to the last element for both. What does that mean? So in these examples, you can see the IDE at the end. And you can always refer to this table for all of this: phosphide, sulfide, chloride, well, not for all the nonmetals, nitride, oxide, and even the polyatomic ions. So let's get started. Okay, I'm gonna number my solutions. So for number 1, I have to make this tiny, unfortunately. We have potassium iodide. The first thing we need to do is to identify the charges. Potassium is K. So K has just a plus, so it's plus 1. So K 1 plus. And then we look for iodide. Iodide is I minus. So it's just I 1 minus. Then that's the first step. Identify the charges. Then we drop the symbols and just keep it. Drop. Now we swap the symbols. So swap these two, but as I'll show you a different example because this is not needed. Then reduce. When reducing, remove all the number ones and common factors. I'll show you an example of a common factor later. So Therefore, it's just Ki for potassium iodide. For number 2, barium bromide. Barium is over here and has a charge of 2 plus. So we have to write Ba 2 plus. Then we have bromide, which is Br, bromide, Br, minus, or just 1 minus. Now, once again, drop the signs and the numbers. Just leave it Ba2 and Br1 respectively. Swap the positions of the numbers, Ba1, Br2. Lastly, reduce any common factors and number ones. So it's just Ba, Br2. So the answer for number 2 is Ba, Br2. Something like this. Alright, now it gets to the tricky part for numbers 3 and 4. Nickel 2 chloride. Well, we're gonna just have to go here. So some of the transition metals unfortunately have more than one charge, and as you can see, it has nickel 2. So we just go by nickel 2's charge, so nickel 2 plus. So let's write that in the solution. Ni, right? 2 plus. Followed by chloride. Chloride is Cl. So chloride is over there. So it's just Cl 1 minus. Once again, drop the numbers. Then swap the location. And finally, reduce if needed. So just clear out the 1 and make this NiCl2. Okay. Hopefully not too overwhelming. It's a little confusing, That's why I'm trying to go slow. 4. Manganese 4 oxide. Let's find manganese. It's over here. And as you can see, it's manganese IV. So Mn4+. Oxide is oxygen, and it has 2 minus. Once again, drop the numbers, swap the locations. Sorry, what was I doing there? And then now we can reduce, because as you could see right here, there's a 2 and there's a 4. That is what you call a common factor, and you must reduce it to Mn1 and O2. And since we reduce any ones, we also remove the 1, giving us just MnO2. It gets, well, surprisingly, it gets even more complex with number 5 and 6. Now, if you look at it, it doesn't seem like these are elements. Hydroxide, acetate, what are those? It's called a polyatomic ion, and I've checked, and most of this should be a non-metal. So treat these as non-metals. And since these are metals, strontium and aluminium, that means we have a metal plus a non-metal. Therefore, these numbers 5 and 6 are ionic, and we do not yet need to use the prefix system. Okay. So, for aluminum hydroxide, let's first look at Al. Al is over here and has a charge of 3+. Al 3+. And then we have the hard part, which is finding hydroxide. These are thankfully alphabetically ordered, and we have hydroxide. So we're just gonna put this in parentheses, OH, and then have the negative 1 minus charge outside. Then we do the same thing again. Step 1, drop. Step 2, swap the locations. Step 3, reduce. And that's our final answer. Al, then in parentheses OH 3. Let's do number 6 now. Number 6, strontium acetate. Strontium acetate, we have to find strontium, which is over here. Strontium has a charge of 2+. Then we have acetate, which is here, and that is a long formula, unfortunately. So you want to put everything inside the parentheses. CH3, COO. Also, just CH3COO. Now you want to put this in the parentheses, and a very, very crucial rule: these numbers inside the parentheses never ever change. Never. If those numbers change, that will change the polyatomic ion, which you don't want. So just put the charge outside. This is 1 minus, as you can see over here. Then we do the drop. The swap. And then we just reduce. Right there. That's our final answer. I'll green box it. Oops. Okay. Number 7. This time it's the same as number 3 and 4, but this time we are using polyatomic ions and transition metals. So you can tell by the remember that these always have a positive charge, so we can immediately say that number 7, copper 2 plus, and we want to find what's this one? Sulfate. Sulfate F-A-T-E is here, not sulfite, sulfate. So we have we want to put that in parentheses already. That is SO4 2 minus. SO4 in parentheses 2 minus at the end. Okay. Here we go. So first, once again, drop. We don't need to swap because they're both 2 anyway. And since they're both 2, we can just reduce that to 1. So swap, then we reduce. This is the final answer for number 7. Number 8, mercury 1 oxalate. So we got Hg from mercury and then 1 plus from the 1. Then we find oxalate, which is over here, C2O4 2 minus. So that's in parentheses C2O4 2 minus. So we do the drop. And then we do the swap. Then we don't need to that's a swap. Then we don't swap. Then we just remove the one over here, and then we reduce. So we don't need to reduce anymore. This is the final answer. Number 9. Number 9, this is where we can finally say that these are covalent, because once again, your first thing to do, you always want to analyze the elements being involved. So it's nitrogen and oxide. Nitrogen and oxygen, both non-metals, which means this is finally the first one where you can use the this one. So what do we have here? We just have nitrogen, dinitrogen. So therefore, dinitrogen is just 2 because di. And pentoxide, pent, is equal to 5. So it's just O5. So I just put di equals 2, pent equals 5. Last but not the least, number 10, we got pentaphosphorus chloride. So phosphorus, phosphide, and octafluoride, both non-metals, and therefore it's also an ionic bond. Oh no, sorry, not ionic, covalent bond. So therefore, we can just put P and then a fluoride. So pent means 5. Yeah, penta means 5, pent 5. And octa or oct just means 8. So we just put that. Penta is 5, oct equals 8. There you guys have it. That's all the solutions for the from word to chemical formula. Now I'm gonna now use the reversed. We'll do reverse doing for this once we're ready. So I'll be back. I'll take a breather. That's a lot of stuff to take in, guys. So take a break. I'll be back once I'm ready. Okay. So once we did the naming to formula. How about formula to name? Well, seeing as they're just a reverse process, we can also apply the same process but reversed. Let me explain. So first, let's identify what this is. Barium. Barium is here. And it's obviously a metal. How about this one? N. Nitrogen. Nitride. Nitrogen. Here. Nitrogen is a non-metal and barium is a metal. Metal plus non-metal is equal to an ionic bond. Ionic bonds do not require any prefixes, so just name it. So first, copy the first element's name, and second, like the raw name, and then second, we have nitride over there. Copy that. And that is the first one. Let's try the second one now. Sodium, Na, is a metal. P, phosphorus, is a non-metal. Another metal plus non-metal. That is another ionic bond, and thus we can ignore the numbers. We do not have to add any prefixes. So we can just add sodium. It's P, so it's phosphide. Phosphide, right? Good. Now, for numbers 3 and 4, this is going to be a little bit complicated. So this is where we have to add our backup solutions. So we have copper and chloride. Copper, chloride. But we know that copper is unfortunately one of those elements that have more than one charge. And we need to figure it out how. And yes, once again, we have chloride, which is also a non-metal. So another metal plus non-metal. Still ionic and still does not need prefixes. So what you want to do is, let's label this number 3 and copy the formula. CuCl2. We're gonna reverse do this. So first we're gonna put a 1 over here to indicate there's 1 copper. Then we swap again Cu2Cl1 and pull those numbers back up. Cu2 plus, because metals have plus bond, and Cl1 minus, because non-metals usually have the negative charge. Cu2 plus and Cl1 minus. Since we have Cu2 plus over here, we can now for certain know that this is copper 2. So we put copper over here, in parentheses 2 in Roman numerals, and chloride. Next, Cr2O3. Chromium is once again one of those metals that has more than one possible charge. So once again, we're gonna do the same thing what we did here, but in reverse. So copy first the item Cr2O3. Then we don't need to reduce. Swap the numbers. Pull the numbers back up and add the charges. Cr3 plus and O2 minus, does that match up? That does match up. So Cr2, we're now certain that this is Cr3 plus, so it's chromium 3. Chromium 3. Oxide. Once again, ionic bond does not need prefixes. Now we're going to add the polyatomic ions now. Okay. So first we have to okay. First we have to find the NH4. NH4 is sulfide. It's kind of hard to see it from here. NH4, ammonium, there, ammonium. So these are positive polyatomic ions, and they do still seem to be, yeah, they still do seem to be. That seems to be what do you call this? Since this is positive, I believe it's treated like, yeah, it is treated like kind of the positive charge. Yeah, because there's no prefixes here. I know that there's no prefixes here. I've seen the answer key. So we're going to do number 5. We actually can simplify this to just 1. So we can just simplify this to 1. And since they're both 1 anyway, so we can cancel this out. This becomes 1. You can just immediately put ammonium, right? Ammonium, yes. Ammonium. Then sulfide, right? Sulfide, yes. Not really sure how that works, but the answer key does say that. So yes, if we're dealing with a polyatomic ion plus a non-metal, that's the case here, I guess. So yeah, that is, we only do use prefixes in the truly like the covalent bonds. So same thing here with calcium. What's that? CiO2, CiO, 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 CiO. CiO2 is, hold on, hypochlorite. It's hypochlorite, which is here, CiO. So here we have calcium. Let's try to simplify this. Number 6, I believe. Calcium. Then we have CiO2. Is that 2? Yeah, 2. So we're gonna put Ca1 there. So we have Ca2, CiO1. Then we just bring them back up. Ca2 plus CiO1 minus. Yep, there we go. So I can confirm, yeah, based on this one, I guess these positive polyatomic ions somehow act as like a metal. That's why this doesn't need, yeah, this number 5 does not need a prefix. So it works kind of like a metal. So yeah, this is the final formula. So we know that it's calcium. So just calcium hypochlorite. This isn't really needed, actually. You just need to recognize the pattern, but this is just for safety checks. So next is nickel, and then we have NO3. Now, this time we're mixing polyatomic ions with transition metals. So we need to actually do this now. So, nickel. Then we got NO3. NO3 is equal to nitrate. NO3. NO3. Then, yeah. Okay. So, NO3. Oh, NO3 too. I'm sorry. NO3, and then we have 2 here. So, once again, we're going to have to, put the number Ni1 here. Then we have to maintain the NO3. Then swap the numbers, so it becomes Ni2 and 1. Pull up back the numbers, N2 plus NO3 minus 1 minus. So Ni2 plus means that this is nickel 2 nitrate. Yes, nickel 2 nitrate. Nickel 2 nitrate. Same thing here. We're going to do this again. We just need to find what SO4 is. And SO4 is sulfate. So Fe2SO4 3. Fe2SO4 3. Once again, swap the numbers. So Fe3SO4 is retained and 2. Bring up back the numbers. Fe3 plus SO4 2 minus. So we're just going to check if that's 2 minus over here. Yes. And this is... Oh, sorry. That's... Sorry, this is sulfate and I wrote it down. It's... Right? Hold on. Yeah, SO4 sulfate. Yeah, just was making sure. So this is indeed iron 3 sulfate. Iron 3 sulfate. Numbers 9 and 10, let's check. Selenium, Se, and chloride. Both nonmetals, so we can just use the prefix system. You can add mono here if you want. It's okay to not add mono, but if it's the first element, it's optional to add mono. So we just put selenium, and then chloride with 2 is dichloride. Di. We now add the prefixes because these two are nonmetals and that makes a covalent bond. Covalent bond uses the prefixes. Lastly, N for nitrogen, and Cl7, chloride. Once again, 2 nonmetals. That means we use the prefixes and they are covalent. So N2 is dinitrogen. And Cl7 is heptachloride. And wow, we actually got through all of those. And I provided solutions when I kind of needed them. So yeah, you can take a screenshot of these for your references if you want. And that was actually tiring, but finally, we finished the longest, well, not really longest section. There's another math section, unfortunately. So yeah, we'll have to deal with that as well. But for now, we're down to our last topic, chemical reactions. The video is almost 2 hours long, by the way. So yeah, let's keep going. Well, we're here. After 1 hour and 38 minutes approximately, we've arrived at the final destination. And this is the final slide that I'll be making. If you're still here, incredible. It's all about chemical reactions. And chemical reactions are just simply when atoms are rearranged to form new substances. So, what are these, well, evidences that we can see that there's a chemical reaction? So the first one is precipitate formation. It happens when you react to two substances. The reactants, I forgot to write that down. Hold on. Reactants plus reactant equals product. So yeah. So it happens when two reactants and then the product, it starts creating either gas or solid. These gases and solids are called precipitate. And that is one of the evidences for a chemical reaction. Next is any sign of color change. This is very self-explanatory. As well as gas evolution. Gas evolution is just when gas starts to form and bubbles start to emerge. And lastly, temperature change. Once again, very, very straightforward. Temperature change. Now, we have to talk about the law of conservation of mass. That mass is not created nor destroyed. We can use this in balancing chemical equations which have two forms. The word equation, where it's like this, but more importantly, the skeleton equation, which we'll be using like this. As you could see, 1 Al plus 2 chlorine is equal to 1 Al and 3 chlorine. So clearly, something's not right. To fix this, we can add a numerical coefficient to each side to balance it. And we're going to be doing that later. By the way, here are some of the, when balancing chemical equations, you may see these. And S for solid, L for liquid, G for gas, and AQ for aqueous. So these are not required in the formula, but if you just see them, I guess you could just ignore them or at least know what they mean. So before we solve for this, I'm just gonna discuss the types of chemical reaction. So the first one is combination or synthesis, where two or more substances form one complex compound. As you could see over here, I color-coded it. It's A plus B turns into AB. The example is 1 carbon plus oxygen gas, so that's 2 oxygen, is equal to 1 carbon and 2 oxygen, or carbon dioxide. Next is the opposite of combination, is decomposition. It's when one complex substance, in this case CaCO3, breaks down to two simpler substances. Now this one is a bit more complex, so I'll explain how we got here. So as you could see, we have a calcium over here. And this calcium went here. Then we have carbon. The carbon went here. Then the 3 oxygen went 1 over here and another 2 over here. So in total is 3. So this is an example of decomposition. So it's not really direct, but you get the point. As you could see, there may be division of atoms of the same type through multiple substances. Then we got the single displacement. So it just replaces an element replaces another element in a compound. So here we have zinc, and then you have Zn, then we have copper's SO4. But then the copper and SO4 get separated. Then the Zn is now with the SO4 plus copper. So as you could see, it's just color-coded almost the exact same. So A is your zinc, B is your copper, and C is your SO4. I don't know this, unfortunately, but I hope you get the gist. As you could see, the SO4 over here used to be attached to copper, but now it's attached to zinc. So that SO4 replaces another element in a compound. Okay, then the most complex one is the double displacement. It's where two compounds exchange the cations and there's two completely different compounds. So as you could see, we have the barium that used to be connected to the chlorine, but is now with CO3. Then you got the potassium, which used to be connected to the CO3, but is instead now with the two chlorines. So by the way, this is technically two potassiums because 1K times 2 is 2K, and 1 chlorine times 2 is 2 chlorine. Lastly is combustion. It happens when hydrocarbon reacts with oxygen to create heat or light energy. So whenever you see C and H on one side, that is immediately a type of combustion. So when there's just hydrocarbon, there's supposed to be oxygen here in both sides. I'm so sorry. There's supposed to be oxygen, and right, there's supposed to be oxygen here, and then if the oxygen is enough, it will either cause a complete combustion where there's CO2 and H2O, or incomplete where there's no CO2. So yeah, you can just look for CO2 and you can determine if this is complete or incomplete combustion. So, and lastly, let's finally talk about factors affecting reaction rate. First, we have to increase the surface area. What do I mean by that? So when you increase the surface area, you can actually lower the activation energy, the minimum energy to start a reaction. because by exposing more surface area, you allow the whatever is reacting, the reactants to get exposed to the other reactants. So therefore, it creates a quicker, a more faster reaction. Next is when you increase temperature. When you increase temperature, it creates more particles moving, because remember, heat creates energy, and energy makes particles move faster. Faster particles, faster reaction. Next, you try to lower the gas. You try to lower the gas temperature, which is kind of contradictory to the last factor I've told you, but it actually tells us that by lowering the gas temperatures, if you lower the gas temperatures, it creates slower particles, but it increases the concentration. So, since you lower gas temperatures, it's just saying concentration. And once again, the more concentrated the reactants are, the faster the faster it will be reacting, because there's more particles reacting. Finally, you can just simply add a catalyst. A catalyst just speeds the reaction up, and it does not interfere with any of the reactants. So those are the four factors affecting reaction rate, and that's the activation energy for you. Now, this technically would be done because we have the evidence of chemical reaction here, the law of conservation of mass, types of chemical reaction, and factors affecting reaction rate. But I do have to take it fully. So what I'm gonna do, we're gonna have one last problem solving. Yeah, I know it's been long. It's been a long day for me as well. I've been recording for 6 hours by this point. So, without further ado, let's just finish this so you can finally rest. So, first one, let's do number 1. So we just ignore the aqueous and stuff. So we have Al plus FeO. Ooh, that's not good. Fe and then O equals solid aluminum oxide and Fe. So unfortunately, this is the sad part about these equations. There's no efficient method. There's no efficient method to solve these. You can try the table. I can show that to you, but it's just not effective for me. So, and I can't really teach it properly. So what we could do is just use, some inferring. So as you could see, we have one oxygen here. We could just use trial error. So we have to fill this in with a blank number, like here. There's a blank here, and there's a blank here for Fe. Same thing here. There's gonna be a blank plus Al blank there. So we know that there's at least 3 oxygens. 3 oxygens. So therefore, the minimum for this one, since there's only 1 oxygen, is 3. Now we have satisfied the three oxygens. Now we have 3 irons now on this side. 3 times 1, 3 irons. So to balance that out, we also need to add 3 here. So we have 3 irons and 3 oxygens. Now lastly, we just need to balance the Al. We have 2 Al here, so we have to put 2 Al here as well. So since this is just blank, we put 1. So let's check. 2 Al here, so we have 2 Al over here. Then we have 2 Al over here. We have 3 Fe over here. Another 3 Fe over here. And then we have O over here, and then we also 3 O over here. So as you can see, we have 3 and then O, and it's over here as well. So this is the correct balanced chemical equation, and let's color code it so that we can tell what is the type of reaction. So you have 3Fe over here, 3Fe over here. Let's then use blue. It's not really the cleanest, but as you can see, there's 3 reactants involved, and that is single displacement. So I'm just going to use a shortened version. So there's single displacement. Okay. Second, I'll actually do it in the box now. So we have, I have to thin it. So Na2O is decomposed into solid sodium metal. So Na, blank Na, plus O2, blank O2. Now, first and foremost, let's start with the sodium. Let's start with the oxygen first. So as you could see here, we only have 1 oxygen on this side, but there's 2 oxygen here. Meaning that to balance it out, this number has to be at least 2. 2 times 1 oxygen is 2 oxygen. And now we just need to fill in this. And since we already have a fixed number here for this side, we can just do 2 sodium times 2. So that's 4 sodium. So that is the answer we're looking for. And it's already stated here. So it's decomposed, and therefore it's decomposition. Next, we have solid AlBr3, aluminum bromide, reacted with plus blank K2SO4, was that? To form this KBr and wow, that's a complex one. Al and SO43. So this is definitely a very complex one, and I think just by the looks of it, as you can see, there's 4 elements. This is definitely a double displacement. So what can we do? Well, we can start first with the bromine. We can start first with the bro. So we can actually start with this one. So we know that this number should be a minimum of 1. However, as we could see over here, it has to be, let's start with the SO4 because that's the most direct. So there's 1 SO4 here, but there's 3 SO4s there, meaning the minimum for this is definitely 3. Now we need to figure out how much this is. So how much this one is, the KBr. So K2, that's 2 potassium times 3, that's 6. This has to be at least 6 because we have 6 potassium here. Therefore, we also need to find, Al2. We also need to find what number is this. We have 6 bromine here. And then we also have 3 bromine here. 6 divided by 3 is 2. So let's check if that's correct. We have 2 aluminum here and 2 aluminum there. We have 2 times 3, that's 6 bromine here and 6 bromine here. We have 3 K2, so 2 potassium times 3, that's 6 potassium. So that's there. Finally, we have SO4 here, 3 SO4. And it's right there, 3 SO4. So yeah, this is the correct balanced chemical equation. Next, we have nitrogen gas, N2 plus H2. sorry, H2 turns into NH3. First and foremost, we can see that there's seems to be a little bit of a discrepancy here. We have H3 here and we have H2 here. So we need to keep doing factors until we meet on a common number. So we just do 2, 4, and then 6. So therefore we did 1, 2, and then 3. Therefore this is 3. But this also means that this is a minimum of 2. So from there, we'll erase this. Then now we have to supply, we then have to supply the 2 nitrogen that we have here. Thankfully, it's balanced, so it's just 1 and 2. So 1 and 2 plus 3H2 is equal to 2 NH3. And I'm not so sure if it's obvious, but it's actually just an example of combination. And finally, for the last question and the last problem solving of this very, very, very long guide, if you're still here, well, I'll probably give you a sticker if you show me proof if you've made it here. Comment Pikachu if you made it here, I guess. Anyway, propane gas C3H8, make sure to put the blank, and oxygen gas O2, blank O2, reacted with each other, producing CO2 and H2O. So, first and foremost, we know that we have to somehow supply at least a factor of 3 oxygen. So, at the very minimum, this is 3 because there's a O2 here and an O here. We need to make sure it's divisible by 3 so that we can separate it. We can separate it properly. So it has to be either 6 or it has to either be 3, 6, or something divisible by 3. So if we then the C3H8, we have to try to balance it as well. Knowing that we have the 3O2 and the 3C here already, let's try to use 1 first. So this will come out balanced. This will come out balanced so far. But we run into a problem here. We still have to do a 1C. We have to deal with the H8 here. And right now we're already out of oxygen. So we need to go with a higher number here. So let's try using 4. No, let's try using 5. That gives us 10 oxygen. 10 oxygen. And we use 6 oxygen here. So we have 4 oxygen here. So we also have 8 hydrogens here. So after a lot of trial and error, let's check if this answer is right. So we have the 1C3 here. We also have the 3C here. We have 8 hydrogens. This is also 8 hydrogens. We have 10 O2s, 6 of which are here. 3 times O2 is 6 O2. Then O times 4 is 4O. So 6O plus 4O is equal to 10O. Therefore, this is a balanced equation. And this is pretty obvious that it's complete combustion. And with that, well, if you made it through all that madness, well, congrats, really. Congrats. I estimate that it takes around 3 to 4 hours to get to this point, probably. And you worked hard. You worked hard to get here. I mean, assuming you didn't skip anything. If you made it through this entire guide, well then, props to you. You're definitely a very hard working person, to say the least. I've been recording nonstop basically since 3 p.m. and if you're still here, then you just watched my longest ever study guide, and thank you for all the support. 500 plus views, 80 watch hours, 21 subscribers. Means a lot to me. Means a lot. Take care of yourself and good luck on your ETAs. I really do hope this helped. And once again to the class, I did fulfill my promise. Once again, as I said, it will be out Friday night. And if you check the date right now, it's still Friday night. So yep. Thank you so much for sticking to the end. And I will see you on the next guide. See you there.